Okay, after a break, then let's come back in the section 2. We're going to discuss the properties of the definite integrals. Okay, the first one we have already explained before, right? If the function f(x) is equals c, which means the function is a constant c, so the definite integral equals c times b minus a, right? C times b minus a. No matter this c is a positive or negative constant, and here b usually is greater than a. The upper limit is greater than the lower limit. That is number one. Second one, okay, when we take the definite integral, the sum of two functions, that means you take the definite integral for each, okay, for each. Actually, this is very similar to the differentiation part. If you take derivative of fx plus gx, that means you take derivative of f and g separately. This is called the some property which applies the same in the differentiation and the integration part. Okay, kind of linearity. Okay, linearity, and this one is the constant multiplication again. We still call constant multiplication again. So times c, okay, times the constant c in front of the function. So you either do stretch or shrink. Okay, if c is greater than 1, then you do stretch. If c is a number between 0 and 1, then you do shrink. Or if c is a negative number, you just put a different sign, put an opposite sign for the area. So this means we do the stretch and shrink based on the function f, so which is the constant times the function. So you can move the constant outside, which applies the same in the differentiation part and as well as the limit part. It's a constant multiplication, right? So those properties actually are similar to the limit and the differentiation part. That's why when we study those limit and differentiation part, we give the name. Okay, this is the sum rule, right? Sum rule, constant multiplication. And of course, if we have fx minus gx, it's the same, right? Just becomes minus. It's the same actually. Yeah, that is the difference rule in the differentiation part. Now here this table shows more. Okay, this table shows more. Okay, now number one, let's go through one by one. Number one, the order of integration. That's what I said. Usually the lower limit a, which is less than the upper limit b. If we change in this way, if we switch the b and a, so that equals minus from a to b. Okay, from a to b, which means if this one from a to b is positive, then b to a in definite integral, that is negative number. So with different sign. Okay, that is how we switch the lower and upper limit. And again, here a to a, especially a to a. Think about the region we formed from a to b. That means the width is b minus a, right? It's b minus a. You form some region. Here, especially from a to a, actually means no region formed. So it's empty. Of course, the area is 0 from a to a, right? Any formula you get like that, from a to b x dx, the formula is 1/2 b squared minus a squared. But when b equals a squared minus a squared, that gives 0, right? This is one example when fx is x. It applies to any function fx. A to a actually is 0 because no region formed. So the area, of course, is 0. Okay. Number 3 is the constant multiple rules we are talking about. It can be k or c, it doesn't matter, but we just set up this one as the constant, right? Number 4, the sum and difference rules. Here. we mentioned, right? We explained. And the additivity, okay, additivity based on the definite integral. If we have the limit, if we have the definite integral from a to b plus b to c, it's the same function, right? It just means you take the region or under the function fx from a to b. This part means you take the region b to c. What is the sum of those two? That means you add the bound, you add the lower and upper limit. A to B, B to C, of course it's A to C. That forms the region under the fx from A to C. So the area from A to B plus B to C equals A to C. We will use the graph to illustrate this one, okay? And those two, okay, the max mean inequality and the domination, okay, the domination series, it's not required in our textbook, okay, it's not required in our textbook. So we will skip those 6 and 7. Now let's use graph to understand some rules, okay. Part A, 0 weights interval. It's zero, it's A to A, right? The lower and upper limit. It's A to A. Actually, it's just 1 line. It's just 1 line. No region formed. Then what is the area? Of course, it's 0, right? No region formed. The area of this region is just 1 line. Then it's 0. Spatially, this is a special case. Okay, constant multiple. Constant multiple here we choose k equals 2. K equals 2 actually means we stretch this function curve fx, right? We stretch in this way, so we get this curve is 2fx, and then this one denote the area under the function 2fx from A to B, right? All those area actually equals double, okay? Double of the blue region's area. That is what the constant multiple rules means. Sum rule, okay? Sum rule or difference rule, it's also similar. So for example, we take two functions fx and gx. Fx, what is this one? Horizontal line. It's a constant one, right? Especially we took the fx as a constant, the gx as this curve. Then what is fx plus gx? Fx plus gx gives this curve, right? You just shifting this one with some distance, vertical distance, right? So this green color gives fx plus gx. Then this one, okay, the left part, the area under the function curve fx plus gx from A to B, that is all those, right? All those area of the regions. What does this one equals? This one equals the blue, the area of this region, blue region, and the area plus the area of those under gx. Under gx means all those, okay? Under gx means all those, not only the brown color, okay? Under the gx, this part from A to B under gx means all those, okay? And it's the same here. Under 2fx, here the left side means all the area, all the region under the curve, okay? Between the top bounded by the curve and lower bounded by the x-axis. Make sense? So that is the sum and difference rule. Difference rule you can work out in a similar way, okay? In a similar way. The additivity for definite integral. So here from A to B, okay, definite integral from A to B under the function fx. Then this blue part is from B to C. Then what is A to C? Of course, A to C is just this brown part plus the blue part, right? That is we call the additivity. But here be careful. This number B should be the same number. A to B, then B to C, right? A to B, B to C. But if you are talking about A to B plus C to D, then we are not sure, okay? We are not sure because here should be the point B to connect those two. those two areas, right? A to B, B to C. And E and F illustrate the max minimum equality and the dominations. We are going to skip those, okay? If you are interested, you can read about those parts. Now, let's see some example to apply those properties, okay? Properties. Example 3. Use the properties of the integrals to evaluate the definite integral 0 to 1, 4 plus 3x squared. This one. Use the properties of the integrals to evaluate this one. Now, this is plus, right? Actually plus, so which rule we can use? We can try the sum rule, right? We can try the sum rule. We can apply the sum rule. fx equals 4, right? fx equals 4. And the second function equals 3x squared, right? 3x squared. So we let the first part is function f, which is 4, and we know equals 4 is a constant function, right? Gx is 3x squared. Actually, you can let gx equals x squared, okay? X squared, because 3 times x squared, that will be the constant multiple rule, actually, right? Constant multiple rule. So we let fx is a constant 4, function g is x squared. Then how can we rewrite this definite integral from 0 to 1? That is specified the a and b, right? Don't forget, when you write the definite integral, don't forget to write the dx, okay? This part indicate we use the variable x, and it's a necessary term, okay? It's a necessary term. With the sum rule, the lower and upper limit is the same. This is fx, right? Definite integral for fx. How can we write this part? This is 3x squared dx, right? And we can, let me keep those again. We will work out later, okay? How, sorry, should it be 4, not 4x. Should be 4, not 4x. So it should be 4 dx plus second term, second definite integral. We have 3 times x squared. So we can use the constant multiple rule, move the constant outside, right? Move the constant outside. Then, what is the formula for this one? From a to b, if we have the constant c, so it should be the constant c times b minus a. That is the area, right? That is the formula when the function is a constant c. So it should be c times b minus a plus 3 times. By the way, what is this part? This is the area under the parabola. Area under the parabola, y equals x squared from 0 to 1. What is this area? We have already discussed this example at the very beginning of chapter 4. 1/3, right? 1/3. Then we can work out the answer. This is 4 plus what? 5. It's pretty easy, right? Without work out the definite integral. By the way, for some of you, if you studied the definite integral before, or if you know how to find the antiderivative of this function 4 plus 3x squared, then it's easy, okay? Then it's easy. We will touch that part later, okay? But right now we just use the properties to work out. They use some formulas we know to work out the definite integral, and we know this one, okay? This one is 5. What does this definite integral mean? This is the area under the function curve 4 plus 3x squared from 0 to 1. Still, again, actually this is a parabola, right? Some shifting. We do some stretching, shrinking, and then shifting, we can get this parabola. under the parabola, the area under the parabola from 0 to 1, and that gives 5. Okay, that gives 5. So this is one example. We use the rules. Okay, we use the property of integral to evaluate. Now let's see one more. It's about the additivity. Okay, let's repeat the formula for additivity. From a to b, fx dx plus, here be careful, the second one, the lower bound should be the same as the upper bound with the first integral, b to c fx dx. That equals a to c, right? A to c fx dx. Fx dx from a to c, right? And usually we should have this order. Okay, usually we should have this order, but it doesn't matter. It doesn't matter if this lower limit is a large number, and we know that from a to b actually equals minus b to a, like that. Okay, like that. So this, similar to the formula, we know that 0 to 8, even though we don't know the function, it doesn't matter. Okay, even though we don't know the function. From 0 to 8 plus 8 to 10, right? We can form the additivity in this way. From 0 to 8, because it is known that 0 to 10 fx dx is 17. 0 to 8 fx dx, the definite integral is 12. Find 8 to 10. So we know that according to the formula here, 0 to 8 plus 8 to 10, that equals 0 from 0 to 10, fx dx. Now we know that this number is 17 and this number is 12. Then what is this one? Of course, it's pretty easy, right? It's pretty easy, it's just 5. Use the property additivity for definite integral. So it's easy to work out these examples, right? So that will be all the examples we did. And section 2 is a little long because at the very beginning, we introduced the definition of the definite integral. And we give some example based on the Riemann sum. And then the second part, okay, the second part will be the properties of the definite integral. And also we understand this definite integral as the area of some familiar shapes we know, like triangle, trapezoid, rectangle, those, right? Now, here are some time left since students asked the question from our quiz, okay? The unequal subdivision. Actually, it's similar to our topic. If you watch the video at Kehan, it should be fine. But let me just simply explain those, then that will be easier for you to work out the examples, okay? To work out the quiz questions, okay? The quiz questions. Let me pick one. Let me pick one example one example we did before to illustrate this unequal subdivision. Okay. Unequal subdivision. Let's just use the example the parabola. Estimate, it's about the Riemann sum, okay? It's about the Riemann sum. So we did estimate this one, x squared dx, using Riemann sum. Using Riemann sums, right? So here, what does this definite integral mean? That is the first example we discussed before. the under the parabola x squared from 0 to 1, right? From 0 to 1, using the Riemann sum. And what we did before is from 0 to 1, we divided into 4 rectangles. Okay, we divided into 4 rectangles. We use 4 rectangles to estimate, and the equal weights. Okay, the equal weights case is each weight is 1/4, right? Each weight is 1/4, and if we calculate the R4, which means you choose the right endpoint. So that will be, this is 1/4, 1/2, 3/4, right? So that will be the function value at the 1/4 when you choose the right endpoint. So the first rectangle will be the function value. We take the function value 1/4 squared, that is the function value, times the weight. That is the area for the first rectangle when we choose the right endpoint. And plus, when we estimate the second strip, we use the right endpoint to form the second rectangle, which is right endpoint 1/2, then the function value will be 1/2 squared times the weights, right? And then the third one will be 3/4 squared times the weights, again is 1/4. And then how about the last rectangle? Rectangle, we took the height when x equals 1, which is 1 square, right? 1 square times the weights. So this R4, okay? This R4 means the 4 rectangles sum with the right endpoint, right? With the right endpoint. So here, each rectangle, what is the formula to get the area for each rectangle? The height times the weights, right? The height times the weights. And especially in this case, the weights is equal. So that is, with 4 rectangles, we get the weights is 1/4, right? How about the unequal subdivision? Unequal case. Unequal subdivision. Unequal subdivision means here from 0 to 1, okay? It's the same case, but it's not 4 equal weights rectangle. From 0 to 1. Now I might choose 1/3 here, and then maybe 1/2 here, then maybe let me do 5/8. So now this is unequal subdivision, we call it, but we can still form some rectangles here, and here, right? So what is the area? The sum of 4 areas rectangle. Sum of 4 rectangle. We can still form 4 rectangle, but those 4 rectangles, their weights are different. Okay, 4 rectangles area. Now it's still, again, you just take the weights. What is the rectangle of the first weight? 1/3, right? 1/3. And when you choose the right endpoint, it's still, we call R4 if you choose right endpoint. So the right endpoint, the height of this rectangle will be at 1/3 the height, right? At 1/3 the height will be 1/3 square. And what is the weight for the first rectangle? 1/3. And plus the second rectangle's area. The second rectangle is the height when we evaluated at 1/2. So the height will be 1/2 square for the second rectangle. What is the height for the second one? The second one the width should be this length. It's not the equal one. You just use 1/2 minus 1/3. And then how about the third one? The third one will be 5/8. 5/8. At this point, the height should be 5/8 square. And then what is the width for the third rectangle? So that should be 5/8 minus 1/2. And so on for the last one. That is the unequal subdivision we did. But if we are going to calculate the area of the rectangle, it's again the same to figure out the formula height and width. Here the widths are different for each rectangle. Okay, so height, if you choose right end point, it's the same. Okay, it's the same, but the end point change. Okay, the end point becomes 1/3, 1/2, and 8/5. And you need to figure out the thing is weights because the weights change. So that is what we said, unequal subdivision. Also, you can watch some video at Kehan to help you finish those. Okay, that is the first question. If you have unequal subdivision, how can you get the sums of several rectangles area? Question 2. Okay, question 2. The Riemann sum using the midpoint. Okay, the Riemann sum using the midpoint. Again, we can use this example. Okay, we can use this example. So we did the right end point. Okay, we did the right end point. From 0 to 1. Okay, Riemann sum using middle point. We can call it M4. M4. Now let's write those first. Okay, let's write those first. This is if we have middle point means you're still using the equal weights. Okay, equal weights 1/4, 1/2, 3/4. So that means we know that if we choose the right end point, that will be the height. That will be the height when we have x is 1/4. The first rectangle's height will be 1/4 square. Right? The second rectangle's height will be 1/2 square. 3/4 square, 1 square. So right end point using right hand point. Using the right end point. Using the right end point. So the height for the 4 rectangles. We're just comparing the right end point and the middle point. So the height for the 4 rectangles will be 1/4 square, the first one, and then 1/2 square, and then 3/4 square. The last one should be 1 square, which is 1, right? Now what is the middle point mean? Middle point, which means you took the height here. Let me use a different color. You took the height in the middle, okay? In the middle. So here, okay? Here. What is the middle point for the first subinterval? So so the point, okay? The point we can mark in this way. x0 is 0, x0 equals a, x1 is 1/4, and we can use the subintervals notation. x2 is 1/2, x3 is 3/4, x4 equals b, which is 1. Now what is the middle point? What is the middle point for each subintervals? Let me check the notation, okay? We use this one, okay? We use this one to denote the middle point. The middle point for the first interval is x1 bar, okay? It's it's like sample point actually. So here especially, very good question. So here, actually, this is like the sample point xi star, but you choose your sample point, especially as a middle point. So it's general speaking, it's xi star, okay, xi star. And for xi star, as I said, we can choose left endpoint, right endpoint, and especially here, I took my xi star as the middle point. So let's figure out the midpoint for each subinterval. So the first one, we use this notation to denote the middle point in the first subinterval. So it's 1/4. And then x2 bar, which will be between 1/4 and 1/2. What is here? What is here? So should be 3/8. Okay, 3/8. And how about here? How about the third middle point? The middle point in the third interval should be 5/8, I guess. Okay. And then how about the middle point in the fourth subinterval here? This one. Of course, this one should be 7/8. Right? 7/8. So using the midpoint, we can call it M4. Okay, we can call it M4. R4 means we choose the right endpoint. Okay, we choose the right endpoint. Now, to estimate this area, we can choose the middle point to get the 4 rectangles. Okay, so again, here the widths are the same. The width for each rectangle is still 1/4, but the height change. We will take the height when we evaluate the f at the middle point. So should be 1/2 square. So the height for those, if we use the middle point, maybe I can write comparing with those. Okay, there is no need to write M4. Okay. So comparing with the notation here, with my statement here, using the right endpoint, the height are all those. Now using middle point, okay, using the middle point. So the height for the 4 rectangles are changed. Okay, the height, so that will be the height. The first one, for the first rectangle, the height will be the function value evaluated at x1 bar. Okay, x1 bar. And then the second rectangle's height will be the f evaluated at x2 bar. And then the third rectangle, x3 bar. And then the fourth one. So comparing with the right endpoint or left endpoint part, only the height, okay, only the height for the rectangle change. And again, the weights, okay, the weights are all delta x, okay, weights is all delta x. Again, it's still 1/4. So M4 will be the height times 1/4 plus this height times 1/4 plus this one times 1/4 and so on. So that is the Riemann sum using the midpoint, okay, comparing with right endpoint and left endpoint. That's what I said. It's just very similar to our topic. We just have different choice of the sample point besides the left endpoint and the right endpoint. Okay. So we did several examples today. Okay. Now here is a quiz. Okay. Here is a quiz. You evaluated this definite integral. And let me explain a little bit. So here, figure out the function fx. Okay. Figure out the function fx. Here, the function fx will be x minus 1, right? Will be x minus 1. How can you draw the graph? If you can draw the graph, then it's easy, okay? It's easy to evaluate the definite integral. It might be, some people write middle point will be more accurate, okay? More accurate. So I'm going to close the 弹幕, okay? Because we are going to do the quiz. I don't want anyone post their answers as 弹幕 to share with others. So here, fx In this one, the fx is x minus 1, right? How can we draw the x minus 1? You just shift your y equals fx 1 unit to the downward, right? 1 unit downward or 1 unit to the right. It's like that. This is minus 1 and 1, right? From 0 to 3, so it might be somewhere here, right? This is x. Then actually it forms triangles, 2 triangles from 0 to 3. That is how we understand this definite integral. Okay, I will give you 3 minutes to finish this quiz. Okay, and that is all about the lecture today. We finish section 2, and next time we're going to start the section 3.